This lecture is about the concept of causality and what is basically causality and how does researchers in their research design in pharmacoepidemiology or in epidemiology in general look at the concept of causality. This lecture is important for you as pharmacy students or as um, someone studying research to understand how we differentiate between an association observed in a research design and an actual cause effect relationship. You may be already aware that in research, you may find a link, an association, a correlation between an independent and a dependent variable. However, just finding this association should not lead us to jump to the conclusion that A is causing B. In fact, there's two layers of check and balances that should be done. The first layer is asking ourselves, is the association observed is a real association or is it an artifact of sampling procedure? Yani, are we seeing an association that truly exists in the population or are we just noticing something that happened to be existing in the sample and would not be existing in another sample? To answer the first question, if this relationship observed is a real relationship or an artifact of sampling, the answer to that is through testing hypothesis, which was already covered in another lecture. So the first check and balances that you do, the first checking we do is testing using a statistical test, looking at the p-value and declaring if the association is statistically significant, well, la. Now, having done that, the second step is looking at the relationship that exists between an exposure and an outcome and trying to see if we can evaluate it to a point where we can talk about the fact that there is a cause effect relationship. So the first thing we're going to do in this lecture is we're going to talk about the causal models. What are the different causal models? So first off, we're going to start with a definition. شو معناتها cause? What is a cause? What is a necessary cause? And what is a sufficient cause? By definition, a cause is an event, an act, a state which initiates or permits, alone or in conjunction with other causes, a sequence of events resulting in an effect, in a disease. Okay, so a cause is an act, an event, a statement, or something that is going to lead to a certain outcome. As a general definition. هلا, we have something called necessary cause and we have something called sufficient cause. Necessary cause, it must be present for the disease to occur. It doesn't need to be the only playing variable, however. Yani, for example, you cannot have the flu if you're not infected by the virus, the influenza virus. Okay, so the virus is a necessary cause. You must have it to have the flu. However, it's not a sufficient cause. Yani, just the presence of the virus does not automatically mean that you have the outcome. So necessity cause is a cause that have to be present for the outcome to be present. The outcome cannot be present if the cause is not present. Okay? But the opposite is not true. Yani, the cause may be present, however, there is no outcome. Okay? Which leads us to talk about the sufficient cause. A sufficient cause, a cause that only by itself lead to the disease, with or without the presence of other factors. A sufficient cause doesn't have to be the sole cause. So a sufficient cause is a cause that by itself leads to the outcome, but it not necessarily be the only cause. There could be other causes. مثلا injury. If the outcome is injury, falling from the fifth floor is a sufficient cause of injury. Okay, but somebody might be injured from other causes. So sufficient mean the minute you have that cause, you will have the outcome. A necessary cause means the outcome may not occur unless the cause is there. I hope you're seeing the difference between necessary cause and sufficient cause. Okay? هلا, we may have something that is necessary but not sufficient. You may have a cause that is sufficient but not necessary. You may have a necessary and sufficient cause. يعني the minute the cause is present, the outcome is present, and the outcome cannot occur unless the cause is present. And you may have a cause that is neither necessary nor sufficient. So let's look at the second table. In this table, we are looking at X. Sorry, I'm showing you Y. Y as being the possible disease effect. So Y is your disease, and Y has two levels. Either the disease is present, and you have a case, or in a non-case, and the disease is not present. And then you have the exposure as either a present, exposed, or not exposed. Okay, so X is considered as a possible cause factor. And out of this, you get four possible scenarios, four possible uh, different profiles. So on the profile A, this is everybody who is exposed and has the outcome. B, هن unexposed but they do have the outcome. C, they are exposed but they do not have the outcome. And D, they're not exposed and they do not have the outcome. And the note says that if X is a sufficient cause, so let's remember شو sufficient. يعني the minute it is present, the outcome should be present. So let's think about X being sufficient. If the X is sufficient, the minute it's present, the outcome has to be present. معناتها no one should be in the C cell. Okay, so if X is a sufficient cause, cell C is always 0. If X is a necessary cause of Y, شو معناتها necessary؟ يعني Y cannot manifest itself if X is not present. And therefore, if you look at those that have the disease, okay, ما حدا ممكن يكون عنده disease. No one can have the disease and not have X. Okay, so therefore B should be 0. And therefore they say if X is a necessary cause of Y, cell B is always 0. If X is both necessary and sufficient cause of Y, then the cells B and C are always 0. Okay? Alright, so let's look at the next slide. In this slide, we're looking at four conditions under which independent X, يعني exposure, may causes Y. Okay? Variable X may be cause of Y. Now, if X is a necessary cause and it is a sufficient cause, so if X is necessary and sufficient to cause Y, is that's both, then both NXYs are always, X and Y are always present together, and nothing but X is needed to cause Y. X leads to Y. Okay? Both of them will be always present together. In the next slide, we'll have some examples to further illustrate. Now, if X is necessary but it's not sufficient to cause Y, then X must be present when Y is present, but Y is not always present when X is. Some additional factor must also be present. So X and Z lead to Y. Okay. So X in this condition is necessary. You must have it, but you might also need something else. X is not necessary but is sufficient to cause Y, then Y is present when X is. كل ما بيكون عندنا X بيكون في Y, but X may or may not be present when I is present, because Y has other causes and can occur without X. For example, in a large spleen can have many separate causes that are uncorrected with each other. So X may lead to Y, but Z also may lead to Y. If X is neither necessary nor sufficient to cause Y, again, X may or may not be present when Y is present. Under this condition, however, if X is present with Y, some additional factor must also be present. Here, X is a contributory cause of Y in some causal sequence. Like in X and Y may lead to X and Z may lead to Y, and W and Z may lead to Y as well. Okay, so we're going to look at some example and see if we can shed more light. So, an example of a necessary cause, HIV and AIDS. ما حدا ممكن يكون معه AIDS إذا ما عنده HIV. It's a necessary cause, okay? However, مش كل مين عنده HIV عنده AIDS. And we know that. And therefore, HIV is a necessary cause but not a sufficient cause. Sufficient cause, مثل ما كنت عم أقول, falling is sufficient to cause a broken hip, but someone might have a broken hip from something different than falling. Necessary and sufficient, trisomy 21 for Down syndrome. Every time you have trisomy 21, you have Down syndrome, and every time you have Down syndrome, it is caused by trisomy 21. Okay? هلا neither necessary and sufficient. Gonorrhea, for example, for pelvic inflammatory disease. It's worthwhile mentioning maybe at this stage that many of the causes that we see in pharmacoepidemiology and in epidemiology in general are neither necessary nor sufficient. Which takes us to something called contributing cause. It's any cause that contributes into a cluster of causation that leads to a sufficient cluster cause. So it's a contributing cause. It's a cause that cluster with other to lead to a sufficient cluster. So if you look at the second slide, that might become a bit clearer. All right, so here we have a cluster of causes A, B, C, D, E. We have another cluster of causes A, B, F, G, and H, and finally A, C, F, I, and J. Now, every cluster by itself, a cluster, is considered a sufficient cause, cluster cause, or a causal pi. Okay, kill pi is a sufficient لحالة. لحالة is enough, but notice that a pi is not made only of one factor, rather an aggregation of factors. Okay, and since we have more than one pi, this means that none of the pi's is necessary. Okay, none of the pi's is necessary, but every pi by itself is sufficient. Now, this is looking at the pi as a cluster. Now, if we start looking inside the pi's, you will notice that in every one of these pi's, the letter A is present. Like none of the pi is complete unless A is present. And therefore, we can conclude that A is a contributory cause, but however, it's a necessary one as well. So A is a necessary cause. لأنه without A, none of the pi's will be complete. However, if you eliminate B, eliminating B would break this pi. It will break this pi, but we still have that pi that is still there. So we still have the disease occurring, or the whatever, the outcome occurring. If you were to delete E, then this pi would uh, would would uh, would 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 not be available anymore, so it will not exist anymore. However, these two pi's will still be existing and leading to the outcome. Okay. Um, so A could be, for example, a genetic predisposition. B could be smoking. C could be lack of exercise. D could be exposure to a chemical component, and E could be age. F could be certain risk activity, etc. Okay, so you will notice that as these elements aggregate together, they create a sufficient pi, and that sufficient pi by itself is causing the outcome. And therefore, نحن when we study in research a factor, so if you come and you study نقول factor G, okay, to see if factor G is associated with the outcome. And now that we understand that they are causal pi, now you understand that G alone cannot be associated with the disease unless it is present with A, H, B, and F. So if in your population that you're studying, the phi A, B, F, H, if these other elements of the pi exist, the pi now is complete and the entire pi is leading to the outcome, and therefore you can observe an association with every one of the letters with the outcome. However, if in the population you're studying, F does not exist, is a F is a chemical exposure, for example, and where you're doing your study, ما في F, or F is pollution, and the study is done in a place where there's no pollution, and therefore F is deleted, hence the pi is not complete, and hence the pi is no longer a sufficient cause, and therefore this pi is not able to lead to the disease, and therefore you will not be able to see a link between G and the disease, and you will conclude that G is not associated with the disease. And that kind of explain why in certain studies they find one element to be associated in the disease, whereas in other studies, the same element is not associated because that element لحاله is a contributing cause, and it depends on the presence or absence of other elements to be able to constitute its causal pie. So these were three different sufficient causal mechanisms. مثل ما قلنا. The disease could be cancer, it could be anything, and the components could be smoking, genetic factor, environmental, age, etc. And we talked about them. Okay, so as illustrated by the figures, every mechanism involves the presence of many components. If one of the components is missing, the circle will not be complete, and thus the disease will not occur. We also noted that only A is necessary for all circles, thus A is a necessary cause for the disease in absolute term, whereas if E was absent, then the first mechanism would not be complete, but the disease could still occur following mechanism 2 and 3. Following this reasoning, one can understand why some studies would find a relationship between disease X and risk factor Y, yet another study would not find it. Maybe another contributor factor Z was present in the first study but not in the second study. So just because an exposure is associated with a disease, it doesn't automatically mean that the exposure is causing the disease. There are always alternate explanations why the exposure is associated with the disease, such as bias, confounding, chance. At the beginning of this lecture, I talked about chance. We addressed that using statistical testing. Bias and confounding are addressed through other mechanisms, which we will address in different lecture. But what matters at this level is that we want to talk about criteria that have been developed by Sir Austin Bradford Hill for assessing causation, and that was in 1965. He proposed a list in a landmark U.S. Surgeon General report called Smoking and Health in 1964, and the list is the following. He talked about the strength of the association between the exposure and the disease. He talked about the consistency in the repeated analysis. He talked about specificity of the case and effect, the time sequence of exposure and outcome, temporality. He talked about biological gradient, plausibility and coherence, experimental evidence, analogy with existing literature. These are the 8 criteria for assessing causality. So every time you're looking at an exposure and an outcome, and you want to see or you want to evaluate if this association or this risk factor can be thought of as a cause, then you need to think about these criteria. In the following lecture, or in the following, slides, I will be focusing on part of these criteria, and these are the criteria that I will discuss in the following slides. So first, let's talk about the strength of the association. How do we evaluate how strong is an association between an exposure and an outcome? Well, you could be comparing two groups, and you're looking at the presence of the disease in the non-exposed group versus the presence of the disease in the exposed group, and the more the difference is bigger, the stronger is the association. One thing you could do that we will also cover in our future lecture is you can calculate relative risk and odds ratios. وكل ما relative risk والodds ratio is bigger, كل ما the strength of the association as a criterion is met. However, you have to bear in mind that if the association is weak, okay, that is not a signal of no causality. Okay, مش كل مرة بيكون في causation the association is very strong. Sometimes بيكون في causation and the association is not that strong. It's a mild or weak association. So number one, as the strength of the association, كلمة أو كلمة, you have a better case to argue causality. However, the reverse is not true. Second is biological credibility. Biological credibility معناتها the suspected cause-effect relation is enhanced if there is a biological mechanism that would explain the exposure increases the risk. Okay, so في عنا knowledge, medical knowledge that can explain why the exposure is causing the outcome. So the relation between heart disease and increased risk of uterine cancer is credible since estrogen causes endometrial proliferation. I'm sorry, this is not hard. This is HRT, the hormone. Um, Another example, again here we should mention that just because our medical knowledge has not covered the topic in details, and thus the lack of knowledge about the topic should not be considered as a non-credibility. So smoking and coronary heart disease, the evidence was compiling many years before the mechanism could be understood. Consistency is number three. The cause-effect relationship is enhanced when many studies conducted by different researchers or different researchers on different groups of population in a different setting using variety of methodologies in different geographical areas and cultural background arrive at the same result. Yani over and over studies, repeated studies are leading to the same conclusion again and again and again. Smoking and CVD and CHD, lots of studies with different designs, all were pointing towards the association. هلا for consistency, inconsistencies of study should warrant caution in interpretation of the result. يعني ولما بيصير في عندك multiple studies and some of the studies are saying في association, some other studies are saying no, there is no association, some studies saying well, maybe in one group there is. So لما بيصير في contradictory results, that could be seen as a factor against causality. That could be argued as evidence against causality. However, I should point out that these studies, before you start piling them up and see that they are contradicting one another, you should be able to assess their quality, evaluate how good they are, make sure that they're all of equal importance. حتى ما يصير في conflictory information coming from weak studies as compared to strong studies. كمان on consistency, but as mentioned in meta-analysis, when considering multiple studies, one should consider the direction, effect, and sample size, as the lack of power could be reason why an association is not detected. So that is like what I was just saying, إنه مش دايما لما بتلاقوا إنه a lack of association is not consistency. It could be that the study itself is a weak study. Temporality is a very important criterion for causality. This is where you're saying that the exposure came before the outcome. Obviously, that's a very logical thing. But also, it's not about coming before, but coming before with enough time. Yani temporality is about what comes first and how long before. Okay? So exposure should precede the outcome by a period of time consistent with any of the proposed biological model. It is difficult to establish, especially if it takes a long time for the disease to develop, and temporality is typically established by cohort studies and RTCTs, yani studies that are considered longitudinal in design. Dose-response relationship, some people I think call this biological gradient. This is where the higher the presence of the exposure, the more you see the outcome. So, في dose-response relationship, and that's a good criterion unless you reach a certain plateau. يعني مثلا smoking and نقول the presence of coronary heart disease. The more people smoke, the higher the risk of coronary heart disease. But once you hit a certain limit where you are a heavy smoker, so once you're smoking 1 pack or 2 packs or 3 packs, خلاص you hit a certain level, then the risk will not budge that much. خلاص you plateaued the risk. So the risk of the disease increases as the level of exposure increases is an evidence of the cause-effect relationship. Death rates from CVD is highest among heavy smoker than moderate smoker than non-smoker. So that's a good example of a dose response. Risk of endometrial cancer increases with the dose of hormone replacement and duration with dose. So dose response where the presence and the duration come in. Both of them are considered dose response. But one should always consider that there might be another factor that is causing this apparent dose response. As smoking increases, the risk of hepatic cirrhosis increases. In reality, it's because those who drink alcohol also smoke. Also, one might consider the leveling off the phenomenon. So هذا leveling off حكيتكم عنه, plateauing. أما هذا has to do more with confounding, which we will also talk about in a separate lecture. The last one is experiment, meaning that probably the best evidence to establish cause-effect is using experimental study, which is not always ethical. Obviously, when you're doing an RCT for a drug, That is your best evidence to say that my drug is causing the outcome to be reduced or the outcome to increase, depending upon what your outcome is. Um, but however, for things like smoking and coronary heart disease, you're not able to test for using experimental design. So we focused on few of the elements. Let's go back to the Bradford Hill criteria, which one we did not focus on. So we talked about the strength of the association. We talked about the consistency in the repeated analysis. Yani we're getting same results from different studies. Specificity of the cause effect. This we did not talk about it, and I think according to Bradford Hill, this is like this disease is mostly seen in association with this exposure, which we know nowadays might not necessarily be true. Time and exposure and outcome. So temporality حكينا عنها انه the exposure has to come before the outcome and with enough time. Biological gradient هيدي اللي قلت لكم اسمها dose response. Plausibility and coherence. This is the that there is a biological model that can explain why we're seeing the outcome. Experimental evidence through RCT. Analogy with existing literature. If you have another disease that resemble your disease, that is caused by an exposure that resemble your exposure, and therefore فيك تشبه بيناتهم. مثلا لنقول smoking and lung cancer or smoking and A عم تشبهها exposure to asbestos and fibrosis of the lungs. Okay, so بنقول في analogy في something that resembles it, so we can support the idea that this is causing that. So this concludes this lecture about causality. In a nutshell, حكينا عن cause. What is a cause? What is a necessary cause? What is a sufficient cause? What is a causal model? كيف a pie by itself could be sufficient لحالة. However, the element inside of it are not sufficient nor necessary, or some of them could be necessary. And what happens when one of the element of the pie is removed? The entire pie is no longer existing. And then we moved into talking about the elements of assessing causality using the Bradford Hill criteria, the 8 or the 7 or the 6 حسب نحن حكينا على كم وحدة منهم in this lecture. I hope you found this lecture helpful.